All right, this is going to be Precalculus lesson 7-1. We're talking about identifying rational functions and vertical asymptotes. So before we begin talking about rational functions, we need to talk about what they are. So what do you guys think? What is a rational function? Could you point to something and say, hey, that's a rational function, or generate one on your own?
Doesn't use imaginary numbers?
It does not use imaginary numbers. That is very true, yes. Can you write something that is a rational function, though? So rational function, generally it just means you have a ratio. So ratio. That's the key word. This means that you usually will have something that looks like x minus 3 divided by x plus 2. You have a ratio there. You have a fraction. If you don't like the word ratio, you can write fraction underneath that. And then by doing that, now we have a fraction, because I made an underline there by accident. But generally speaking, this is the key thing to take away, I guess, from this section, is this. It's always going to be a polynomial divided by a polynomial. You will have a variable in the numerator and the denominator. And I use polynomial here really generally, anything that has an x in it, or a variable in it, if it was in terms of t or y. So I just want you to be able to say, okay, that is a rational function. So I'm going to write out 3 different functions, and you need to tell me if they're rational or if they're not rational. So identifying. I wonder if the Yeti microphone can hear my fan on my computer, because it's under a huge load of doing a bunch of things right now. All right, let's try number 1, number 2, and number 3. So I'm going to say, actually, I don't want them that close to each other, but we're going to have 3. We're going to have 3 functions because they're going to be ratios, so they're going to take 2 lines apiece. Let's try f of x is equal to x squared plus 2x plus 1. All of this divided by x squared minus 1. If you think it's a ratio, write ratio. If you don't think it's a ratio, write not ratio. Number 2, we'll do a different letter. We'll do like g of x. We're going to say that's going to be x plus 1 divided by, we'll do 2 to the power of x minus 1. And the last one, number 3, it's really annoying. Number 3, let's do h of x. That's going to be equal to, we'll do x minus 0.5, all of this divided by x plus 2, x minus 3. All right, do you guys need more time to think about whether or not they're a rational function or not, or should we go through these? Got it? Arrow, need some more time? Okay, yeah, number 1, give me thumbs up, thumbs down. Yep, it is, so we'll write ratio, or rational. Perfect. Number 2? So thumbs down? And arrow? Wasn't sure. This one actually is irrational. And the general reason is because there's a variable in the denominator and a variable in the numerator. And what about number 3? It is, yeah, it is irrational also. Oh man, I'm feeling the lag for my pen. All right, so there's some kind of cool things when you graph rational functions. So this section, let's title this the strange graphs of or rats. We can abbreviate. The strange graph of rats, rationals. All right, so I'm going to draw what you might see, especially on the AP test, too, a type of rational graph. So you have your coordinate plane. We'll take up a bit of room here because we don't have too much more after this. This is probably one of our biggest day of notes, though, in a while. All right, so go ahead and make a dashed line somewhere up here that's horizontal, and then some other dashed line. We'll do like one right here that is vertical. These will help us to make our graph when we sketch it out. All right, so I'm going to make my graph so that it has this curve that gets closer and closer to this dashed line without actually hitting it in this direction, and gets closer and closer to this horizontal dashed line without actually touching it. And very similar on the bottom right, but there's going to be one exception. So again, it'll get closer and closer to this axis. It'll come up here, and then all of a sudden there will be a random hole in the graph. And then it will continue out this way, getting closer and closer to that horizontal asymptote. So those dashed lines, they're not actually the function. They're just there to help us build the function. We should actually label what our function is. So our f of x is this blue line. It is also this blue line. It is the same function, not two separate functions. So our vertical asymptote, I could write that all out, but being the mathematician I am, I'm going to be lazy, and I'm going to say that is our vertical asymptote, VA. And our horizontal asymptote, again being lazy, horizontal asymptote is going to be this dashed line right here. And the technical term for this whole thing here is called a hole. I know, very precise. So in AP Calculus, we'll eventually be talking about what type of thing this is. The main thing that you should take away from this is a discontinuity. So that this whole thing, I drew a picture of it. That's not a zero, but that's a picture. That hole is a discontinuity. I was doing good. I was nice and continuous, and then all of a sudden, I was not continuous anymore. I was not continuously leaving my pen on the paper. I guess it's technically another discontinuity here. You can't keep your pen on the paper through this vertical asymptote. You have to pick it up and then keep drawing again. That's a good...
If you fold it.
Ah, yeah, that's true. If you folded it, you could do it. I'm going to say that maybe you're doing this in wood shop, so it would be impossible to fold the piece of wood. But I guess paper is more typical.
You should see those hydraulic presses.
The hydraulic press channel. Have you guys seen it? What? You guys have never seen the hydraulic press channel? All right. After this lesson is done, we're going to watch like a 5-minute episode. It's basically a channel devoted to like people donating them weird things, and then he puts it in his hydraulic press and destroys it. It's pretty hilarious. The best thing... Oh, never mind. It's opinion-based. Let's talk about some important facts from our graph. So the first thing is that I'm not going to say rationals. I'm always going to say rats now. Rats are not continuous everywhere. Are we okay with this word continuous? It just means you have to leave your pencil on the paper, assuming that the paper is not being folded or anything special.
Well, I don't like it because at the state spelling bee, I got out spelling it wrong.
All right. I'm sorry. But we're okay mathematically with the definition of continuity? being continuous? Perfect, okay. Number 2. So rats can have holes. They don't necessarily need to have them. Can have holes. And in green here, I'm going to talk about the calculus term that you guys should start getting accustomed to. These are called removable discontinuities. Continuities. Which means, this is a fancy way of saying, if you could somehow get rid of that hole, then it would be continuous. Then I would be able to use my pencil to stay on the paper the entire time. If I just removed it, then it would get rid of the discontinuity. A vertical asymptote, by the way, is not a removable discontinuity because there's no little thing to take away. This is like a big thing that I would have to take away. I can't just remove it. Let's talk about number 3. There are 4 facts. Rats can have vertical asymptotes. What? I don't care about your Java update. Rationals can have vertical asymptotes. They can have that dashed line where it gets closer and closer to that line. And number 4, very similar to number 3, is that rational functions, rats, can also have horizontal asymptotes, but don't necessarily have to have them. One thing that we do know is, number 1, they are not continuous everywhere. There's at least one of these things happening, usually multiple things. All right, we have one more slide, one more section. Looks like we're done writing, yes? All right. And this is how to find vertical asymptotes. So I'm just going to say finding Nemo/story/vertical asymptotes. All right, so let's give ourselves an example. So we'll do an example on the left, and we will do the steps on the right. What are we doing in this example? So here's our example. We're going to do some function of x is equal to 2x plus 2, all of that divided by x squared minus 1. Okay, Camtasia's trying to tell me that it's done exporting. All right, step numero uno, factor. So when I factor this thing, what is the numerator going to be? Oh my god. I'm so sorry. I did not mean to put parentheses there. Can you please erase your parentheses? It's supposed to be 2x plus 2.
Oh, I didn't put parentheses.
Oh, lucky dog. You have no erasing.
But I use a pen, so it's probably good.
That is really good. The pen assumes that both the teacher and the student don't make any mistakes.
Yeah.
2x plus 2, like that. Sorry. Now we can actually factor, because it hasn't been factored for us. All right, what is that numerator going to be? Just shout it out.
2x plus 2.
If you factor out the greatest common factor. Or maybe you said it right, but you...
Yeah,
2
2x plus
2 times the quantity of x. Yeah, plus 1. So 2 is the greatest common factor that I factored out. And the denominator factors to what?
x minus 1 times x plus 1.
X minus 1, x plus 1. Perfect. Difference of squares. You do have to memorize difference of squares all the time on the AP test too. All right. So we are on to step number 2. Step number 2 is to look for bottom factors and top factors that cancel. Or that don't, sorry. Let me write that out correctly. Look for bottom factors that don't cancel. Bottom factors that don't cancel. I can spell don't correctly. Don't cancel. Don't actually cancel anything out, but just look for the ones that don't cancel. And then the answer here is what? Which one doesn't cancel?
X minus 1.
Yep, so we're looking at x minus 1. We're looking at you. You're going to be the reason that we have a vertical asymptote. And finally, step 3. So the vertical asymptote, if I'm pronouncing it correctly, is going to be the 0 of step number 2. Which is a fancy way of saying set it equal to 0. That's not even a fancy way of saying it. It's just another way of saying set it equal to 0, and then you'll have your vertical asymptote. Sometimes it'll be hard. Sometimes the bottom will be set to a polynomial that doesn't cancel out, and you'll have to set that equal to 0. So in this case, we'll have x minus 1 equal to 0. X is equal to 1. So in conclusion, we have a vertical asymptote at x equals 1. And again, that vertical asymptote on a graph looks like this. At x equals, what do we say on this one? At x equals 1, so it would have been on the right. On this case, you can't have any point. It goes off to infinity and negative infinity, depending on what side you come from. All right, that is all we have. Go ahead and do your summaries.